Hey everybody, this is Professor Ross, and in this video we're going to talk about what impacts strength of evidence. We've got a couple of different ways we can measure strength of evidence with the p-value or a standardized statistic, and today we'll look at a few of the different things that can affect those measures and either strengthen your strength of evidence or weaken it. So let's take a look at a few notes here. And as we are taking a look at what impacts strength of evidence, take note our key learning objective remains trying to learn about using the logic of statistical decision making. And strength of evidence is one of those keys to making decisions in statistics. So, quick review. How do we assess strength of evidence? We've been talking about using the 3S strategy, calculating a statistic, simulating what we call a null distribution, simulating what we'd expect to happen if the null hypothesis were true, and then judging strength of evidence by comparing those two things. I encourage you to pause the video for a moment and try to answer these two questions. Why is this very strong evidence against the null? And what changes would make it weaker? So, this is very strong evidence against the null hypothesis because the null hypothesis is suggesting that we should be seeing a proportion of about 0.15 over in here. And our simulation of what would happen if that were the truth suggests most of the time we'd see results something like this. Whereas the statistic we actually saw was way out here. So, as far as a p value goes, we see almost no chance of seeing a result like this statistic way out here, 80%, if the truth were really that it were 15%. Another way to think about it is we are many, many standard deviations away from the mean predicted by the null hypothesis, or the proportion predicted by the null hypothesis. Many standard deviations away from that, indicating we have something very different than what the null hypothesis would suggest. So, what are some things that could make this weaker evidence against the null? There are a few possibilities we could consider, and we'll get more into depth in each of these, but hopefully some of these seem natural to you. One is that if this weren't 80%, if it were down here somewhere. So if instead of this, we saw a result that was over here, now we see something much more likely to happen if 15%, the null hypothesis claim, is the actual truth, and we'd have much weaker evidence against the null. So if our result ends up being closer to what the null predicts, then we see weaker evidence. Another possibility could be that this null distribution didn't turn out to be only down here. What if it were wider? So it's going to be a little harder to sketch what this might look like, but what if these bars were wider and wider out here like this? Now it would seem to be something that might be a little more reasonable to happen rather than what we see here, which is almost no chance of this happening way out here. Um, so those are a couple of the different ways we could see some weaker evidence. We're going to dig more into these kinds of ideas with another specific example. So here's another actual research article: Todorov, Mandasoka, Gorin, and Hall in 2005 reported on a study that they did. They asked people to look at pictures of two US Senate candidates and decide who looked more competent. And then they took all the people's results and they calculated which of the two ended up being uh, selected as the more competent person overall by all the people they interviewed. Then they took those results and they compared them against the actual winner. So the data we has was the person who looked more competent, did they win the race or not? And it turned out that they predicted the winner in 23 of the 32 races. So the person who looked more competent to people ended up winning more of the time. I encourage you to take a look at all these things we've got in symbols here. Pause the video for a second and see if you can explain what each of those means. Let's go through these each. The first one is the null hypothesis is that pi, the proportion of success here, predicting the winner correctly, is 50%. Now, why should that be the null hypothesis? Well, in this case, it makes sense. There are two people competing. One looks more competent, one does not. 50% chance that the more competent looking person wins the race. Alternative hypothesis is that the proportion of success, the more competent person winning the race, is greater than 50%. We suspect, our researchers here suspected that the person who looked more competent might have an advantage in their race and end up winning the race more often. So greater than 50%. P hat, that's the proportion of success in our data. And here 23 of 32 were successes. So 23 divided by 32 would give us 0.71875. N is 32. There were 32 observations, 32 races that they looked at to see if the competent person won the race. The p-value is very small, 0.007, so a little bit less than 1%. What does that p-value mean? There's a little bit less than a 1% chance of us seeing a result like we actually saw in our data if assuming this null hypothesis is actually the truth. So there's almost no chance of seeing this many races getting picked correctly if it really is just 50-50 whether the competent person is going to win or not. So we saw something very rare and strange if this null hypothesis were the truth. That suggests our evidence is very strong evidence against the null hypothesis, and we would reject it. Let's talk about how the Z statistic gives us similar kind of read on the evidence we have. The Z statistic is 2.43. What is that saying? That tells us how many standard deviations from the mean of the null distribution our result is, about 2.5 standard deviations away. In this case, positive, so above the mean of the null distribution. Is it real typical to be over 2 standard deviations away? Nope, that's actually pretty rare. We see it's not quite out to the 3.0 range where we would claim we have very strong evidence, but we do have strong evidence against the null hypothesis. So p-value gives us very strong, z-statistics gives us strong. They're both pretty strong evidence against this thing, so we want to reject it. So one of our conclusions is reject the null hypothesis, but we should always say with our conclusion, what is that telling us about this situation? That is suggesting that the competent, looking at the faces and deciding who looks more competent, that's not just a 50-50 chance of who's going to win the race. In fact, the person who looks more competent is statistically significantly higher chance of winning the race, which is really interesting. So let's talk a little bit about this strength of evidence. Once again, we saw strong to very strong evidence against the null. What might impact that strength of evidence? What if instead of they had predicted 23 of 32, what if they had only predicted 20 of 32 races? You can see now all this stuff remains the same until we get to p hat, which is now lower. It's a lower proportion of success in our data here. We're only seeing 62% of the time we've predicted correctly. And what happened to our p-value? Now, instead of being very low, it's actually quite high. It's above 10%. What happened to our Z statistic? Instead of being so big, it's actually a lot smaller number. So visually, we're only 1 and 0.39 standard deviations away. Our result, instead of being farther out here, has now moved closer into the middle of things. We've got more going on out here, so our p-value is higher. We're less standard deviations away, so our Z statistic is lower. If you recall back to what this tells us about strength of evidence, if a p-value is above 0.10, above 10%, we have little to no evidence against the null hypothesis. Same idea with the z-statistic. It's below 1.5, little to no evidence against the null hypothesis. So if this were actually the scenario, we would say, hey, we don't have much evidence that this is better than just 50-50, better than guessing. And so our conclusion would turn out to be the opposite. So we can see that one of the things that has a big impact on strength of evidence is what your actual statistic turned out to be. If your statistic is closer to what the null hypothesis claims, 62% is closer to 50% than 71%. So that means we've got weaker evidence against the null hypothesis. So that's one big thing to take note of. When we have a statistic closer to the null hypothesis claim, we tend to have weaker evidence. What if they had included more races and still predicted the same proportion? So this is what if everything else had stayed the same? They had still predicted 71% of the races correctly, and but instead of just 32 races, they had checked out maybe 128 races or even 256 races. It might seem like, hey, same statistic, we should have the same strength of evidence. That's kind of a natural idea. However, something interesting happens a lot with our null distribution. What seems to be different about these three null distributions? So if we ran the simulator and we did it for 32 or 128 or 256, what seems to be the difference? This one is much wider, this one's narrower, and this one is really skinny. Now, how does that change strength of evidence? Well, let's put a little line on each of these where our 70% prediction ends up. So here it would be right around here, and you can see that we'd be a certain distance from the center here. You know, it turned out being 2.5 standard deviations. And we got a few dots outside of it. What happens when we go here? Whoa. Now there's nothing outside of it. And if we think about what the standard deviation might be like here, it's probably something more like 3 to 4 standard deviations away. Stronger evidence when we have a bigger sample size, all else remaining the same. Does that hold true when we get to even bigger sample? Look at this. 0.7 is way far away now. This would be many, many standard deviations away. Even stronger evidence. So in general, the main idea here is bigger samples, stronger evidence against the null. This is one of the main reasons why researchers tend to want to try to get as big a sample as possible. They want their test to be able to give them strong evidence if it's appropriate. So if there really is something different than the null going on, they want to get stronger evidence against that null. So they try to go for larger sample size. All right, so we see if our statistics change, a statistic changes, that gives us different strength of evidence. If our sample size changes, that gives us different strength of evidence. And here's another idea to contemplate. What if they hadn't just assumed choosing by facial appearance would do better than just guessing? So at the beginning of the study, they set up two hypotheses: null hypothesis, just guessing, 50-50 chance. But their alternate said, we think the long run proportion is greater than 50%. We think looking at whether they look like they're competent will help us pick the race correctly. But that might not be true. What if the person who looks more competent actually tends to lose the races more often? They assume that wouldn't happen. That's called a one-sided alternative. They said, hey, we think it's going to be greater than. On the other hand, we can set up studies where we're not sure. We don't know. It might turn out greater or it might turn out less. We call that a two-sided alternative. We symbolize it this way with a not equal sign. And that would be read as, alternatively, we think the long run proportion is not 50%. Might be greater, might be less, we don't know. What happens to our strength of evidence in those scenarios? So the left is the one-sided alternative, and you can see why it's called one-sided. Only one side is shaded in red here, whereas the two-sided alternative has two sides shaded in red. Here on the left, we assume that everything is going to turn out higher than 50%. On the right, we said, well, we don't know. It might be higher or it might be lower. So we include evidence both higher and lower with the two-sided alternative. What does this do to our p-value? For a one-sided alternative, the p-value, and the one I'm looking at here was about 0.1074. When we simply include the other tail, it's the same size. This is saying 10% of my results are up here. When I include both of them now, it's about 20% of the results. So what happened to our p-value? Went from 10% to 20%. It doubled. What does that mean with a p-value if we have a higher number for a p-value? That means that we have weaker evidence, right? The strongest evidence is the lowest in that little table. Below 1% is the strongest evidence. As we go higher in that table, we have weaker evidence. So a two-sided test, all else remaining the same, will always give you a p-value that's weaker because it will be doubled. Now, it might not cross one of those borders, like if your p-value was originally 2% and it doubles to 4%, it might still stay in that strong evidence range, but it's still a little bit weaker evidence when it's 4% rather than 2%. Why would anybody ever use a two-sided test then? In fact, researchers use the two-sided alternative a lot. In fact, it's supposed to be the one you use by default. Why is that? It's because the one-sided test is embedding an assumption. So when the researchers set it up and they did a one-sided test, they said, we assume that looking at their faces and deciding if they look competent is going to help us guess more correctly. That's an assumption that they've embedded in here. It may be a good assumption. They may have some reason to think that. There may be logical reasons or prior research that suggests that, and that's okay to use a one-sided alternative when you have some good reasons to support that. On the other hand, if they came in saying, we don't know if this is going to help improve, improve how well we predict the races or not, then really the fair thing to do is to choose the two-sided test. And so that's why it's considered the default option to do a two-sided, because you're not embedding that same assumption in there. It also is important to note that when you do a one-sided test, if that assumption is wrong, the entire thing backfires in your face. So for example, here, if they would have assumed it was higher and then it actually turned out to be lower, their p-value would include all of this stuff, a p-value that would be through the roof, it would be around 90%, right? And that kind of is a backfire. So if you embed this assumption in and then your assumption was wrong, in some sense, it kind of ruins the whole study. So you have to be very careful when you do a one-sided test. We tend to encourage two-sided tests unless you have very good reason to use a one-sided. But it does give us weaker evidence. The p-values will be twice as high. All right, so in summary, we can see that we get stronger evidence when our statistic is farther from the null parameter pi. We get stronger evidence when we have a larger sample. That's one of the reasons why statisticians like to get as large a sample as possible. And we tend to get stronger evidence when we have a one-sided alternative.